Hello friends, welcome to Devrat Knowledge Villa. You are watching our English video series of operating system and learning Deadlock. Today's our topic is safe state, and safe state is one methods for deadlock avoidance. Actually, for the deadlock avoidance, there are three techniques. First one is safe state, second one is resource allocation graph, and third one is Banker's algorithm. So guys, by implementing this three strategy, we can avoid the deadlock. Now the fundamental is why we want to avoid the deadlock, because actually there are various methods for handling the deadlocks, that is prevention, avoidance, detection, recovery and ignorance. We have already discussed the deadlock prevention. So guys, if you are still remain to watch our videos about the deadlock prevention strategy, so you can click here at top right corner on I button and you can watch that videos. Now we are discussing deadlock avoidance. So prevention and avoidance are the pre-strategies before system reach into the deadlock states, and detection, recovery and ignorance are the post strategies after system reach into the deadlock state. Let's start discussing safe state without wasting us time. So what is the safe state? If I will say about the safe state, so a state is safe if the system can allocate resources to each process up to its maximum in some order and still avoid a deadlock. My dear friends, I know very well you are not able to understand this para because actually this healthy para is written by Peter Galvin. So don't worry, I will make this para very easier for you. Look like, suppose there are three processes, process P0, P1 and P2, and we have a 12 number of resources R0, R1, R2 up to R11. Get it? So now out of these 12 resources, process P0 requires 10 resources, process P1 requires 4 resources and process P2 require 9 resources. So think, now is it possible to allocate all the resources, because total requirement is 23, but we have already 12 resources available. Get it? So don't worry, it is not necessary all the process require all of the resources at the same time. Get it? Maybe during the execution some resources are required in earlier stage and some resources are required into the post stages. So let start allocation. First we are allocating few resources to process P0. We are allocating 5 resources to process P0. Next we are allocating 2 more resources to process P1, and same we will allocate 2 resources to process P2. Total we have 12 resources, out of we are allocating 5 plus 2 plus 2. It means total we are allocating 9 resources. So out of 12 we allocated 9 resources. So how much resource are remain? So there are total 3 resources are remain to allocate. Get it? Out of 12 we have allocated 9 resources and still we have 3 resources. We can allocate these 3 resources to any process. Now let me make this figure little bit smaller and we will putting this data into tabular form. Let's see, nothing is changed here. These are our processes P0, P1 and P2, and total 12 resources I have put into the tabular form. Process P0, P1 and P2, total 12 resources. Get it? What is the requirement? 10, 4 and 9. So here that is a maximum needs 10, 4 and 9. How much allocation is there? 5, 2 and 2. So let's see here, allocation is 5, 2 and 2. Total allocation is 9 resources. Now how many resources are remain? Total 3 resources are remain. Let's see, total 3 resources are available. Now see here, maximum needs is 10 resources and allocation is 5 resources. So how many requires in further out of 10 if we will subtract 5 out of 10? So here 5 resources still require to process P0. Here requirement of process P1 is 4 resources and system is allocated 2. So if we will do 4 minus 2, so 2 resources are still required to process P1. And same for the process P2, maximum needs is 9 resources and allocation is 2. So 9 minus 2, still total 7 resources are required. Right now we have 3 resources available in our hand. So what we can do, let's start allocating. Suppose out of these 3 resources, let's start for the process P0. So we are allocating these 3 resources to process P0. Get it? Now we are allocating these 3 resources. So total allocation is 5 plus 3. How much resources remain in our hand? No. Out of 3 we have allocated 3. So 0 remain. Now what is the current need? Current need was 5. Out of 5 we have allocated 3. So remaining requirement is 2. Get it? Now let's see what is the maximum need of process P0, that is 10. What we have allocated 5 plus 3 total 8. So still 2 resources are required. For the process P1 2 resources required, for process P2 7 resources still required. Is there any resources on hand? No, there is no resources available. So is it possible to complete any process? No, because all of the processes are require resources, and whatever the resources required by these processes, these resources are actually held by some other processes. Get it? Because total we have allocated 12 resources. 9 resources was earlier allocated and plus 3 resources we have allocated. So we have allocated all 12 resources. So there is no resources are remain to allocate. Get it? So is it possible to complete this process? No, this thing is not possible to complete any process. Get it? So thing is that system may lead a deadlock. Let's try some another way. Let's see, we are starting with the process P1. We are allocating out of 3 2 resources to process P1. So how many resources remain here? Out of 3 2 allocated, so 1 resource is remain. Get it? Now total requirement of P1 is 4 and we are allocating 4. So there is no further requirement of process P1. Get it? P1 got all 5 resources. So definitely after few times P1 will complete its execution. Get it? So after completion of P1, these 4 resources remain free. Get it? And 1 resource was available on hand. So 1 plus this 4, so total 5 resources are available. Get it? Now let's see about other processes. Requirement of P0 is 5 and requirement of P2 is 7. We have 5 resources on hand. So can we allocate these 5 resources to process P0? Yeah, definitely. So we are allocating these 5 resources to process P0. We have allocated total 5 resources. So is there remain? No. Get it? And requirement of P0 was 5. So we have allocated 5. So there is no further requirement of P0. Total 10 resource we have allocated to process P0. So definitely after few times P0 will complete its execution and this 10 resources remain free. Get it? So now we have a total 10 free resources and one process P2 is remained to execute. So total requirement of P2 is 9. We have already allocated 2 resources and current need is 7. So out of this 10, we can allocate more 7 resources to process P2. So there is no further requirement of process P2, and out of 10 we have allocated 7. So there is 3 more resources remain. Now P2 get all 9 resources. So after few times P2 will complete their execution. Get it? So this 9 resource become free. So total 3 plus 9. We have a all 12 number of resources are free and all processes complete their execution. So let's see about the step sequence. In which sequence process executed? First process P1 was executed, then after process P0 was executed, and then after process P2 was executed. Get it? So execution was in sequence of P1, P0 and P2. So we can say that this sequence is a step sequence, and due to this step sequence we can say that this entire state is a step state. Get it? Now let's see with the little bit changes. Here I am making few changes in this example. Let's see what is the requirement of P2. There was 9. Now we are modifying it by 10. We are increasing by 1. What was the allocation of P2? That was 2. We are allocating 3. It means we are increasing plus 1. So total allocation was 9. Here total allocation is 10. And current requirement will remain same, because here 9 minus 2 is equal to 7. Here 10 minus 3 is equal to 7. Total resources available in starting position, here there was 3. Here there are total 2 resources available on hand, because out of 12 we are allocating 10. Now let's start to solve this with the same, like out of 2, these 2 resources we are allocating to process P1. Get it? So is there any remain? No. 0 remain. Is there any further need for process P1? No. 0. So total 4 resources we have allocated to process P1. So after few times P1 will complete its execution and this 4 resource become free. Now in place of 0 we have total 4 resources available in our hand. So if we will look about process P0 and P2, so requirement of P0 is 5 and P2 is 7. So is it possible to complete this process with the 4 resources? No. This thing is not possible to complete these processes. It means we are not able to complete these processes. If we will look, these resources actually held by some another processes in the set. It means it is a definition of deadlock. So after few times this state will lead to the deadlock state, or it will lead to a starvation. So indirectly we can say that if we will able to found any step sequence, no, we are not able to get any step sequence to execute these 3 processes P0, P1 and P2. It means this state of this processes is unsafe state. Get it? So hope you are understanding the difference between safe and unsafe state. Now by concluding this example we can say that a system is in a safe state only if there exists a safe sequence. Yes, true. Here safe sequence is available, so system is in safe state. Here safe sequence is not available, so system is in unsafe state. So this statement is true. A system is in a safe state only if there exists a safe sequence, otherwise not. Let's see. Look about this paragraph. A state is safe if the system can allocate resources to each process up to its maximum in some order and still avoid a deadlock. So indirectly this para is saying like that whatever we have concluded, a system is in a safe state only if there exists a safe sequence. Get it? Both meaning are same. So let's see. There is two state, safe state and unsafe state. Now you are easily understand what is safe state and what is unsafe state. And unsafe state may lead to a deadlock. So for these two states, we can say that a safe state is not a deadlock state. Yeah, definitely safe state is not a deadlock state. Second thing, a deadlock state is an unsafe state. Yeah, deadlock state is an unsafe state. And third statement is not all unsafe states are deadlock. It means it is not necessary all the unsafe states will lead to a deadlock. Don't mind, we will prove these statements in our further lectures. So hope you are understanding what is safe states. If you have any query regarding to the safe state, you can post me in comment box. Thanks for watching Devrat Knowledge Villa. Thank you very much.